So good afternoon, everybody, and thank you for your time this afternoon. So in this session, we're going to talk a little bit about defence applications. First of all, I'll start by introducing my company, Abaco Systems. We're a Jetson partner of NVIDIA, and we've been manufacturing GPU cards and box solutions with NVIDIA for many, many years, all the way back to G73s when we were doing embedded graphics just as pure graphics. And now we're doing package solutions and board level solutions. So we'll talk a little bit about what we do and what our value is. So this session is focused on defence requirements and ruggedization. So extreme ruggedization, high temperature range, high shock and vibration for platforms in naval, aviation and ground. This is where we're located. I'm based in the UK in Toaster, which is quite close to Silverstone. We're actually headquartered in Huntsville, Alabama. So we do manufacturing in the US as well as in the UK. Most of our GPU products are manufactured in the UK, so no ITARs. That's a big issue for our customers, so we manufacture those in Europe. We do all the research and development, manufacture of those products in the UK. In Edinburgh, we've got a Ethernet networking specialization, so we also do networking. So networking is an important part of military ground vehicles and military applications, especially for mobile platforms. So that's very important for us. The other important site for military is in Boston, where we have our high-performance embedded computing center. So our customers are typically doing things like DSP applications, electronic warfare, where low-latency, high-performance algorithms are required. So there's a lot of optimization that go into those algorithms. And we have a whole suite of middleware, which I'll talk about at the end of the presentation, which can help you rapidly deploy a platform to solve your specific problem. So we've got a whole suite of middleware libraries and AI annotation tools that you can use to quickly deploy your application. We'll talk about that at the end of the session. The last couple of sites that we have are in Austin, where we do FPGAs. So you need to acquire high-speed signaling, so A to D conversion. And in Goleta, we have an avionics business as well. So part of what we do is taking commercial technologies. In this instance, it's the NVIDIA GPU Jetson platforms and the desktop chips. And we screen them for high temperature range, for shock, vibration. The requirements that our customers flow down onto us are for military-grade ruggedization. So for ground, that's a mil standard 810G. For aviation, it's DO160. DO254, so those kinds of the qualifications that we see. So they are very, very high temperature range, very high shock and vibration. There's naval tests for salt, fog, humidity. So our box products need to meet all of those requirements, as well as ECM type of requirements. So that's what we specialize in. Most of the products that we do are open standards, so that's important for defense. They don't want to be tied into a specific vendor with a bespoke point solution, so we design to open standards. Most of those are the Vita standards, so VME, compact PCI. Today, with the high-speed signaling stuff, it's mostly the open VPX. With the high-speed wafers on the back, you can get PCIe Gen 3 over the backplane quite easily. It's very achievable, which gives you the high throughput that you need when you're using a GPU. So if you've got a CPU, GPU solution, you need that high throughput to get the performance out of your application. And again, we do a whole suite of box products as well. So let's get into the military side of things. So I'm going to focus my conversation today primarily on ground and autonomous resupply. So that's what I want to talk about. But before we get into that, let's talk a little bit about where we are with ground vehicles today. So I've got this diagram up here of a typical Vetronics electronic vehicle architecture. So you can see the types of things that we have on that. We have everything from sighting systems, which are vision systems, through to ballistic calculation, commander displays, driver displays, gunner displays, data recorders, RF gateways. There's a lot of capability on today's modern battle tank. And there's all sorts of roles where GPUs can be deployed. So there's all sorts of capabilities within the turret and within the base of the vehicle that are required. And again, we need open hardware, open standards to leverage the COTS offerings in these markets. So I'm going to talk a little bit about open standards. So open standards are important for lowering cost, lowering risk, getting interoperability and scalability. There are different standards depending on where you're based around the globe. So if you're in the US, In the ground vehicle market or in the avionics market, you're going to see the Victory standard. You may see the FACE standard. So those are US-centric standards that define the hardware architecture and the software architecture. So they give you a limited subset of connectors, of software APIs, so that can increase interoperability and reduce the cost of ownership and allow you to more easily manage your supply chain and to manage your program or product through to the end of life. In the UK and in NATO, you'll see a lot of mention of the generic vehicle architecture. The generic vehicle architecture was originally an MOD initiative, and it came under the Land Open Systems architecture. So we'll talk a little bit about that, and we'll focus in on that because that's now been adopted by a lot of NATO countries. So Germany are now working to GVA. The Australian government have the Land 400 program. We can talk about that. They have their own version of GVA as well. So GVA is very important for NATO countries, and that includes countries like Japan, South Korea, Australia, the Netherlands. They're all working to this GVA specification. So that's where today's talk is going to focus mainly. So why do we need scalable open platforms? Well, the vehicles that these platforms go on vary greatly, and it can be anything from a quad bike through to a Land Rover or a 4x4, a wheeled vehicle, all the way through to a tracked vehicle. And these are the objectives of the open standards. So reducing the through-life costs, so we've mentioned that already, encouraging interoperability, trying to avoid vendor locking, being able to take your platform off of your tank and put it into your vehicle, so you can maybe have a video recorder that you develop for your battle tank, now maybe you want to put it into your wheeled vehicle. So it's all about increasing competition and reducing costs. And then finally, it's all about technology insertion. So you may deploy your battle tank today, but it'll be in service maybe for 30 or 40 years. The technology that we're going to have available to us in 30 years' time is unknown today. So technology insertion is very, very important and, again, is allowed for and considered within these open standards. So this is the generic vehicle architecture and how it's made up. The overriding standard here is something called LOSA, the Land Open Systems Architecture. And it comes in three parts. The first part is the generic vehicle architecture. Now, this is the part where I see the most opportunity, and this includes wheeled, tracked vehicles and autonomous resupply. So that's where I'm going to focus the rest of my discussion. But we also shouldn't forget the generic base architecture, which is about base networking and overseas bases. And then we have the soldier architecture, which is more about wearables. So man wearables, touchscreen interfaces on the arm, backpack computers, those kinds of things. So we're going to focus in on specifically on the generic vehicle architecture today, which is DEF standard 2309, and look at how we can use that standard and where we can exploit GPUs within the generic vehicle architecture. So here are some of the roles where we can deploy, and we are currently deploying GPUs today. The picture on there is of a video server that uses Tegra processors. So that's a platform that's being deployed today. So we've got various different displays within the vehicle, so we can use GPUs just in the traditional way, just driving those displays. But GPUs today is more about deep learning and AI. So where can we deploy that? Well, predictive analytics, so being able to tag video in real time with information about, maybe car registrations, people, identification, and then being able to mine that later on. So a lot of information is being recorded and stored and being collected in data centers. HUMS, health and usage monitoring, so predictive and analytics to predict vehicle failures, predictive maintenance. We can use AI there. We can use GPUs for cryptographic, securing network interfaces and things like that. Protocol conversion, we've obviously need to compress video as well, so video compression capabilities, H.264, H.265, also very, very useful when you've got limited bandwidth. And then we've got all sorts of different threat detection, situational awareness scenarios where GPUs can increase autonomy. So how big is the opportunity? So I'm just going to focus in on some major programs at the moment. I've tried to put some numbers against those. So if we start at the top, Ajax for us is one of our biggest contracts. So we provide all of the network switches, video server, and computer processors into the Ajax platform. So there's a number of boxes that we provide onto that platform. That's currently going into production now in the UK in Wales. So that's a program that's being trialed now and will go into service in 2020, and that was for 500 new vehicles. If we start looking at the future, then the next thing that's going to come along is the Challenger upgrade. Challenger is due to go end of life in 2025, so there's a life extension program on Challenger where they're going to rip out the old analog architecture and they're going to fit a new fully digital architecture onto Challenger. So Challenger is an interesting opportunity, and there are RFIs out there now for Challenger upgrade. We're going to mention Australia because Australia is spending big at the moment. They've got a major program called Land 400, which comes in 3 phases. Phase 2 of Land 400 is for the Boxer vehicle. That contract was signed and awarded to Rheinmetall Defence about 3 weeks ago at their ground vehicle conference, and that's for 211 new vehicles. And that's a turreted version of the Boxer, so it's a combat and reconnaissance vehicle. So they're going to need lots of AI intelligence, and they've got lots of vision systems for infrared, visible light, situational awareness. There's a whole bunch of capabilities that are going to be required for that program. But that's not the biggest opportunity for Australia. They've just put out their tender pack for Land 400 Phase 3, which is for 450 new combat and infantry fighting vehicles. That program is absolutely huge. That's a 15 billion Australian dollar program, and that's going to be very similar to the Ajax program, and actually the Scout platform from General Dynamics is being offered into that program along with the Lynx, which you can see down the bottom. So that's not been selected yet. That competition is currently running, but that's for the defence industry. 450 is quite a big number when you think of the number of boxes that actually go into these vehicles. And then we're in Germany, so we have to talk about Rheinmetall and the Lynx. So that was announced at Eurosatory. The Lynx is, I was reading on LinkedIn only yesterday that the Lynx is now going to be offered as a Bradley replacement. So Rheinmetall are partnering with Raytheon in the US to offer the Lynx to the US guys. That's very interesting, as well as the Australia and the Czech Republic who are also looking at taking on the Lynx platform. Again, the Lynx is kind of the same class as the Ajax vehicle above, so those two are in competition. The Warrior upgrade, which is ongoing. Again, this is a life extension program that's happening at Lockheed Martin. If we look in the Middle East, there's 490 new vehicles. The VBCI is a next platform. Again, that will have lots of capabilities. Vision systems, that's being offered into Qatar. And then finally, more recently, there's a directed purchase for the Boxer vehicle. This is a non-turreted version, so this is fulfilling a slightly different role to the Australian requirement. And that is a military infantry vehicle, so it's a people mover. And that's for 508 new vehicles, and 60% of the spend on that will be UK spend, just like the Australian Boxer will be first 25 in Germany manufacture, and then the remaining 186 manufactured in Brisbane. So some very exciting programs going around. And again, that's just on the larger platforms. I didn't bother to mention anything under 150 units. So let's talk a little bit about video, because video really is where GPUs can really shine. Where you can see lots of demos as you walk around the shop floor, processing various different video streams. So the reason I put this slide up is a lot of these video protocols and video interfaces service different markets, and the defense market has some very specific and special requirements. Primarily, the cameras can be tens of meters away from the processors. So you can imagine on a main battle tank, the processor may be in the base of the vehicle and the cameras may be on the turret of the vehicle. So a number of meters away. So that rules out some of these protocols. The one that you're going to see and the one that we're going to talk about is gigabit. So gigabit is great for military vehicles. It's simplified wiring, so you can run all of your application code over a consolidated network interface, Ethernet switching. GVA specifies that you can have a 10 gig backbone, so generally there's a 10 gigabit fiber optic backbone going around the vehicle, and then off of that you can hang off all of your processors, your displays, and gigabit is really great. Up to 100 meters cable length, so you've got lots of cable you can put out there, but more importantly than that, they've got the multicast capability. So when you're doing mission briefings on the vehicle, the commander, the gunner, and the driver can all be subscribed to the same video stream. All of those situational awareness cameras can be distributed to all of the displays on the vehicle. So gigabit is really where it's at on ground vehicles, and that's what's specified in the GVA specification. You might see a little bit of HDSDI in avionics, the avionics side of things, but HDSDI tends to be point-to-point, so it's a coaxial cable, simplified, easy wiring, but again, because it doesn't have that multicast capability, you're probably not going to see an awful lot of SDI in ground applications, but you will see it in avionics. So here I've tried to describe a simple use case for where we might be able to deploy GPUs. So in the middle, I've drawn the Ethernet switch. The part of the specification that defines video. So there's the GVA specification for the hardware, for the man-machine interface is called DEFSTAN 0023. For video, there's a separate standard, and that's called DEFSTAN 0082. So inside 0082, it describes 3 different transport mechanisms for video. The first one is raw, uncompressed YUV streaming data, and that's using the RTP protocol. So here you can see the raw RTP video moving around the vehicle. So we have some cameras. The cameras will be talking RTP. They go into the processor. The processor can then send it via the network to the video recorder, where it's then stored on the disk. Now, in this architecture, the bandwidth is very high, so the videos will be compressed either when they're recorded to the disk, or they will be compressed when they go over the radio frequency gateway, which is shown at the bottom. So that is a limited bandwidth interface that doesn't need to work in real time, so then you can do the compression. So that's the first part of DEFSTAN 0082. The second part is JPEG 2000. RTP streaming is also allowed. So, and then if you've got a bandwidth-constrained interface like the RF uplink or downlink, then you can use H.264. But again, you're going to have problems doing that in real time. So those are the 3 parts of the standard. This is the standard you want to have a look at if you want to learn more about all of the different streaming protocols. The standard RTP, if anybody's used RTP, there's also session announcement protocol. Session announcement protocol is not part of the standard for anybody that knows RTP because all of the IP addresses and all the discovery, everything's statically defined in a military vehicle. You don't have a lot of dynamicisms on those streams. They're not started and stopped. Once a camera's streaming, it just streams the whole time, and then you just choose to subscribe to it or not subscribe to it. So RTP is not working with SAP announcements into this standard. So it's quite simple and quite easy to implement. If you want to see an example of the implementation of RTP, I've got a GitHub project I can point you out. I've got some standard C code that implements that protocol, and you can run that on your real-time operating system. You can run it on Windows, you can run it on Linux. In the US, you're not going to see RTP because they have different standards. They tend to favor GigE Vision. So I've redrawn the diagram here showing GigE Vision. GigE Vision has a control and camera streaming channels. It has this concept of channels. So you don't need SAP announcements. It's more dynamic. The reason it wasn't selected for GVA is because there's actually some patents associated. It's not truly open, but it does the same thing. So you're going to see GigE Vision in the US. You're also going to see it in the NATO standard. So the NATO standard is here. It's called PLEVID. The PLEVID standard wholly adopts DEFSTAN 0082 and then says that we'll also allow some extra protocols. So it adds in some audio protocols, and it also adds in it also allows GigE Vision. So in NATO programs, they wholly adopt DEFSTAN 0082 and they add in some extra protocols. So it's kind of a superset of what's defined in 0082. So 0082 is very important, wholly adopted, and then you've got these extra protocols inside the PLEVID standard. So we've got these 2 streaming protocols. They're Ethernet streaming protocols. So this slide, we're going to go just a little bit deeper now and talk about color space, and I'll explain why color space is important, especially for raw video. So let's just give you a quick heads up. GigE Visions use something called Bayer encoding. The human eye is more sensitive to green light than it is red or blue. So if you see the pixels over the side, each pixel is alternating between various different colors, with the green being represented more than the red and the blue. So this color encoding is called Bayer 8. So 8 bits per pixel, but because you've only got the green value, you need to infer the red and blue value from the pixels that surround it. So there's some additional processing involved when you're talking about Bayer, because you have to infer the green and blue. You have to infer 2 of the 3 colors that you need for an RGB color space. So that's how Bayer works. It's very efficient. There are some interesting little artifacts that you can get with Bayer. It's not perfect, but it's very close to the way that the sensors receive and filter the images anyway. So it's very close to the raw sensor, CCD sensor that you have in your camera. Then in GVA, I mentioned we use YUV encoding. So YUV is a broadcast standard. It's used a lot in analog encoding. It represents the color information, the black and white information alternately. And again, the important thing to take away from that is that it's actually 16 bits per pixel required. So if you're streaming these raw protocols, YUV is going to consume twice as much bandwidth as Bayer. So this slide says, well, we've got our Ethernet streaming, but you're always going to have to deal with some legacy stuff. I put this slide on there because there might be some corner cases where you might want to use the CSI interface. Some good news, NVIDIA are supporting the camera that was on the TX1 and the TX2 development kit. So if you were an early adopter and you've got one of those kits and you've just bought your Xavier kit, you can unplug the camera off your TX2, TX1 box, plug it on the bottom of your Xavier kit, run this Gstreamer pipeline, and your camera's going to work. So we tried that out the other day. It worked great. So if you want to start messing around with CSI, it's full Gstreamer support inside there. You're probably not going to be applicable in too many defense cases. This might be applicable if you've got a tracking system or a sighting system where you want to integrate it into the camera, very close to the camera head. This might be useful in some of those kind of corner cases. And then finally, you're still going to come across a lot of analog input out there. A lot of missile systems, a lot of legacy systems out there are still sending analog video in. This is a mini PCI Express card, but it does a lot of analog I/O, and you can buy an adapter to put it into the PCI Express slot. So this is a card that we're going to take a quick look at to try and get some of those legacy systems. So when you're doing a life extension program, you may have to accommodate some analog inputs if they're not wholly GVA compliant. So we put that on there as well. So getting back to the bandwidth, so these slides are slightly out of order. So I wanted to get back to bandwidth because bandwidth is important. This calculation here is showing the resolution. So if you calculate the resolution, so the height times the width, times the color space, times 30 frames per second, you can see that the bandwidth soon adds up. So at 640 by 480, you're only 9 megabytes. But as soon as you get up to HD, 1920 by 1080 in Bayer, you're up to 60 megabytes. You could probably squeeze that down a gigabit Ethernet link. But if you're doing YUV at the same resolution, 1920 by 1080 YUV at 30 frames, you got 120 megabytes. Now you're beyond what's possible on gigabit Ethernet. Now, why is that important? Well, I'll tell you. So gigabit Ethernet cameras are, that's it, they're 1 gigabit. They're not 10, they're 1. But there's multiple cameras around the vehicle, so it doesn't matter whether they're gigabit Ethernet or they're DefStan 0082 cameras. When you've got a lot of them, you're going to have problems aggregating that information. If you've got a situational awareness system with 8 cameras, you're going to need to aggregate all of that information so that you can stitch it together and you can get a situational awareness system that gives you that 360-degree vision system. And that's not accounting for infrared cameras. So you might want to augment your system with visible light and infrared light. The bandwidth soon starts to add up. So all your cameras are going to be gigabit Ethernet. You're going to need an Ethernet switch that aggregates all of that and interfaces with your Jetson platform. So one way you might choose to do that is to aggregate using a 10 gig fibre limit interface. So fibre is mandated under GVA. It's the backbone on the network in these vehicles. So if you tapped into the fibre, you could aggregate all of those camera feeds into a single fibre optic link, and then you can attach your Jetson Xavier module, and then you can do lots of sophisticated things, including pose estimation. You can do people tracking, people detections. There's lots of interesting things we can now do on that stitched image. So I think that's quite exciting, but bandwidth is going to be very important, especially if you're going to want to do this in real time, because as we've demonstrated, it's quite a difficult problem. The Xavier also has very good compression capabilities, so that Xavier could also be driving your RF link. So if you want to download this after the mission, or you've got a battlefield network and you want to start streaming this in real time, as well as displaying it in real time to the commander, you could also be streaming it off the vehicle on your radio frequency battlefield network. So that could also be useful there. So just some more information. If you're going to want to get started with these cameras, GigE Vision, there's good open source support for that. I've been using something called the Arvis API, which is an open source API, so you can get started with that. It's pretty good. There's a commercial one called Pleora. So there's commercial support for GigE Vision cameras. For those of you that haven't come across GigE Vision and USB 3 Vision, they're driverless cameras. So the idea is that you don't need a device driver. Not like web cameras, where every web camera needs a different driver. GigE Vision is a driverless standard, so you don't need device drivers. If it works on your platform, you can plug any GigE Vision camera and it will work. And there's a USB 3 Vision as well, but we don't see that in the standards. So it's a driverless Ethernet standard, doesn't require any additional drivers. So the open source software has one driver, it works with all the cameras. For RTP streaming, some good news as well. There's full RTP support in Gstreamer. Gstreamer allows you to get started very, very quickly with those cameras, and I've provided an example pipeline there. as well as if you come and speak to me afterwards, I've got some good projects up on GitHub where I can get you started with RTP streaming if you want to use it in an embedded operating system or you want to use it in real time. Gstreamer is a real-time video processing pipeline and framework, and I'm happy to talk to you about that as well. So, some good news. DefStan 0082. We talked about the 3 parts of the standard. We can do uncompressed RTP. That's the pipeline I just showed you. It's fully supported, and it interfaces with all of the cameras and all of the displays in GVA, and that's perfect for real time. There's a Gstreamer plugin for JPEG 2000. So JPEG 2000 is trying to do a certain amount of compression and tries to do some bit of lossless compression. So JPEG 2000 is very interesting. And there's RTP encoders in Gstreamer for H.264 as well. So it aligns very closely to what's required in the GVA spec. So the Xavier is looking like a great module for us in those military ground vehicle programs. We took a look recently, and Gstreamer has moved forward quite a bit since the TX2, so they're now on Gstreamer 1.14. I've had a few people say they've had a few issues with video for Linux. Things have moved forward quite a bit, so there might be a few teething problems when you jump on there. It has moved on quite a lot since the TX2, but now we've got better support for the protocols that we need in our defense platforms, so that's good news. Okay, so we've talked a little bit about where the opportunity is. So we've talked a little bit about vehicles and situational awareness, but really the big push both in the US and in the UK at the moment is in autonomous resupply. So that's about taking people away from the front line. It's the last mile of resupply. And the UK is running a competition at the moment to get, it's a 3-phase program. We'll talk a little bit more about that. And these are the scenarios that they talk about for autonomous resupply. So you can see drone applications and wheeled vehicles resupplying troops on the front line. So you can find out more about that competition. I've provided the link below. You can see at the top we've got some of those platforms, and I've got some more information about those platforms. If you're interested in any of those, I've got some data sheets for the platforms. We've got the Titan vehicle, which is the third image, so we've got the data sheet on that. That's a kinetic initiative. We've got the Honda Maria Viking platform, which is the first image. I think the second and third are US platforms. I'll put some links at the bottom to talk about those. But if you're interested in learning what the capabilities of those platforms are, then come and have a speak to me afterwards. So those platforms are really about autonomous delivery of munitions and supplies to the front line. And this is how the program is set up at the moment. So there are people working on these real platforms now with a view to winning some MOD contracts in the future. So the first phase is unmanned carrier platforms, and then increasing the autonomy as it goes through to the third phases. So this is a program that you may have heard about, but of course is a very important part of the program at the moment. So it's really taking people out of danger and away from the front line. So here are some examples of how we can deploy AI. We've got the traditional algorithms that we all know and love. Image recognition and segmentation could be very interesting on those feeds. But I think one of the areas where I'm seeing a lot of interest is in pose detection. So pose estimation, pose detection. Something like the Xavier gives you that desktop performance where you can start doing this stuff in real time, and that's the key to all of this. If somebody's pointing a gun at you, you need to know now, and you need to know in real time so that you can take the appropriate actions to address that threat. So alerting the commander to the fact that he's looking out of the front-facing camera, and meanwhile in the rear-facing camera when someone's pointing a gun at the vehicle. If we can have a GPU doing pose detection and detecting people acting in a threatening way, maybe a group of people have collected at the rear of the vehicle and they start shaking fists or, behaving in a certain way. We can have some autonomous actions kick in to alert the commander that he might want to go and look and take a look at that. Not all of the cameras are visible light, so we have infrared. So infrared is great if you're in the dark or you're operating at night. So that's an example of image fusion, where you take a visible light camera and infrared camera and you fuse it together, and you can increase visibility by fusing those different parts of the spectrum. These vehicles all move, so stabilization is important. You can have gyroscope stabilizing your cameras, but you can also do digital stabilization, and that works very well. It's part of the standard SDK, and the Jetsons can do digital stabilization. Tracking we see more of in naval ships, guns automatically tracking targets. But in ground vehicles, ballistic calculations, so in the turret, actually doing those complicated calculations within the turret can all be GPU accelerated. The issue with putting any Linux system in the turret is firing a gun is a very dangerous thing to do, so it needs to be very precise, it needs to be very accurate, and it needs to be deterministic. So GPUs in the turret are very hard because of the threat to life and threat to loss of life if anything is miscalculated or delayed. So you see a lot of real-time operating systems really doing this stuff in the turrets, but maybe in the future we could see GPUs taking over. So, but yeah, electronic countermeasures and things like that are quite sensitive, and they have very stringent software requirements. And then image correction, so GigE Vision cameras, if you've got a GigE Vision camera, you ever use one, you choose your camera, you choose your optics, you're probably going to get some barrel distortion in there. I know under the TX1 and TX2 it was hard to correct that unless you did it in software. You didn't get any access to the ISP unless you were an automotive tier 1 customer. So the ISP was in there, but we didn't have access to that. But now we've got Argus is the ISP, so now we can address that with Argus, and we can address that. So that's the first thing that you're going to need to do before you start stitching your images together. You need to adjust for the optical distortion on the lenses, and we've got some software that can help you address this as well. Our ImageFlex toolchain helps you do that. We'll talk a little about that at the end. And then finally, situational awareness, where you're bringing it all together now, and you're stitching all of those and giving yourself a region of interest or a long image that you can then see all the way around the vehicle. So how do you then present that to the commander? So we've played around with this is a modified version of Dustin's 2-day to a demo. So we retrained this to do a banana demo recognition. But if anybody's done training, the obstacle here is how do you get training data? Who's going to collect all the training data to do the things that we need to do in defense? I think there were 1,000 images of the banana in 2 days to a demo, but you still don't get. You get quite high, but you want it to be really good. So you really need to collect about 10,000 images to be able to identify the thing that you want to be able to look at. And those images are now classified in the defense environment because the things that you want to look at are probably classified. So who collects that data? Who does the training? So there's a lot of opportunity there to provide services to military customers to help them do that training. Their engineers are used to working in C code. They're not graphics people, and this stuff is quite new to them. It's quite specialized, but there's a challenge there as to who collects that data. If it's all secret, how do you then do the training, and how do you treat that data with a secure secret classification? You can't put it in the cloud, so you're probably going to have to do it on site. So there's a lot of opportunity there for software companies to go in and put infrastructure inside companies to enable them to do all this type of training. So I think there's good opportunity there. So here's some more opportunities. I'll skim over that. You can download these slides afterwards, obviously. So again, we really only, the more I think about it, the more opportunities I can come up with in ground vehicles. So I tried to list a few more just there. So how do we help our customers deploy this stuff? So you can do this stuff in the lab. We can all go and buy a Jetson and do it on our desk, but there's some very stringent requirements that we need to work to get those deployed. So just there's some photos of some of the open form factors that we do. So Open VPX is a great form factor, very high-speed connector, very rugged connector. It comes in two sizes, and we have GPUs in the 3U VPX. 3U is about this size. That GPU there is just a GPU, so you need a second slot to put your Intel processor. So in desktop, you need your Intel and your PCI Express. So that goes into very small packages, one like this on the right. So this uses the 3U VPX. That contains a Xeon processor and an NVIDIA GPU in a box product. The one in the middle is more suited to electronic warfare, radar and sonar applications where you're not size or power limited, so it's a high power, high performance processor. That board there actually has a GPU and an Intel processor on a single card. So I think that's a unique product. I haven't seen anybody ever put Intel and NVIDIA on the same PCB. That's something that we can do as Abaco Systems because we have access to the chip down devices. So that's at the high end as well. So finally, as well as doing ruggedized hardware, we also do some accelerated middleware solutions. So I'll talk a little bit about how you can use that to accelerate your defense application. The toolchain that we have is called Access Advanced Multiprocessing. So we have interprocessor communication libraries. So we use OpenMPI. So our customers are trying to build clusters. There are some customers that will just have a single CPU, but some customers, especially in radar and defense, they may have racks and racks of processors. So you might have 10, 15, 20 Xeon processors all trying to work together on the same problem. So when you do that, managing all of those processors becomes more like an enterprise cluster. So we have interprocessor communication libraries that use MPI, message passing interconnect. We have an open version of that that works with our tool chain that will allow you to build those clusters and run those clusters very efficiently and scale them when you need to. So you may have a system that you've developed for your indigenous market, and you might need a reduced capability version for export market. If you pull out half of the processors and you recompile your code, you can scale it down, you can create an export version at a lower cost, maybe with a lower capability. So scalability is at the heart of what Axis does. New to Axis, we're putting in ImageFlex annotation tools. So annotating your data is really where you're going to spend most of the time. The algorithms don't change an awful lot, but you do need to annotate the data. So we're adding in tools for annotation. Visualization tools are now becoming part of Axis ImageFlex, so visualizing point clouds. So we've got tools in there to do that. And these are some of our standard demos. We've got a visualization demo there that shows you how to do the fusing of visible light and infrared light. So those two cameras actually are at different heights, so they have different perspectives, so you need to correct for that. You need to correct all the ISP stuff. The code wants to be in RGB color space, but you've got Bayer, so just converting from Bayer to RGB is actually quite processor intensive on an ARM processor, so you might want to offload that to the CUDA, to a CUDA engine to do your color space conversion. There's lots and lots of functions in there that are accelerated that are going to help you do this. It seems quite trivial, but actually there's a lot of things that you need to do, and when you're doing it on an ARM processor, you need to do that very efficiently, and again, that's what the GPU is there for. So there's a data sheet on ImageFlex. The benefit of ImageFlex is it's designed to be used by a C programmer, not by a GPU expert. So it's a C API and C++ that can be used not only on Windows and Linux, but also if you have an embedded GPU, you can potentially use in VxWorks or Lynx OS. So there are some embedded operating systems. So it's giving you that portability that you can create the application, run it on a Windows device, and then if you need the determinism, you can port that code then over to something like VxWorks without having to do a lot of work. You know, if you start using OpenCV, you're probably not going to be able to take that code then over into a real-time operating system. So that's the problem that we're trying to solve here. There is a little bit of overlap with those middlewares, but really this is about embedded engineers in the defense sector being able to rapidly jump on this and being able to deploy and build an application very quickly. So the rest of Axis tool chain, this is really our value. We're trying to accelerate the speed to development. We've got lots of code. I didn't even talk about our signal processing libraries. So if you're a sonar or radar customer and you're doing DSP functions, those are very large vectors. And of course, if you've got a vector, then that's the first thing you're going to go after if you've got a GPU, is to try and accelerate that and put it onto the GPU. So we have a lot of libraries that do signal processing. So if you've got an application that requires high-speed signal processing, we've got a lot of libraries that can help you offload that onto the GPU. Those libraries also work with AVX. So AVX 512 is coming now as the next version of the vector SIMD function on Intel. So you can offload that onto AVX if you don't have a GPU. Then if you add a GPU and you've got large vectors, then you can offload that onto the GPU, and the performance just runs away with it. The bigger the data set, the more performance benefit you're going to get using a GPU in DSP. So we have DSP libraries that are all highly optimized for NVIDIA GPUs, and that's CUDA under the bonnet. And then we've got our visualization tools and debug tools. Again, a great way of visualizing your system, identifying bottlenecks, monitoring it in real time. So these tools are designed to complement your existing IDE tools. And again, they're OS agnostic. They're not tied to one particular operating system or one particular microarchitecture. You can run this on PowerPC, you can run it on ARM, you can run it on Intel. So it's a very portable set of libraries that allows you to play around with things. You know, prototype something on an ARM processor, recompile it for Intel processor. How does it perform with AltaVec on PowerPC, with AVX on ARM or the GPU? You can quickly benchmark your code and try and find which architectures are going to give you the best performance benefit. So there's a couple of white papers you might be interested in. There's a GVA white paper that I wrote a little while back, just gives you an overview. So if you want to go and download those, you can. A little bit on deep learning. It's more of an introductory paper, so go and take a look at those. That's really our value. And if you've got any requirements for embedded and ruggedized applications, whether it be in nuclear, so we have some adjacent markets that we work in, oil and gas, deep sea, submersibles, those types of things. We'd particularly like to speak to anybody that has a requirement for ruggedizing Xavier, so we have a plan to ruggedize the Xavier and get that into military programs. If there's any protocols that you think that would be beneficial in a rugged environment, come and have a chat with me. I'm here today with our GPU product manager, Stuart Heptonstall, at the back of the room. So Stuart's here as well, and me and Stuart will be outside we'll be in the room afterwards, so please do come and have a chat with us. I did bring along a little box today, so this was our TX2 concept. So if you want to see what a rugged box looks like with no moving parts that meets the military requirements, we have a box. You can come and have a look and talk to us about that. Yes, and other than that, I'd like to say thank you for coming along today, and I'm happy to take any questions.